Have you ever wondered what happens inside a black hole? First off, a black hole isn't just a big empty space. It's a region where gravity is so strong that not even light can escape. But at the very heart of this cosmic monster lies the singularity. The singularity is a point where our current understanding of physics simply breaks down. Now you might ask, what's inside the singularity? The truth is, no one really knows. The laws of physics as we know them cease to apply. Some theories suggest that all the matter that falls into a black hole gets compressed into this infinitely small point. Others propose that singularities could be gateways to other universes or dimensions. One thing's for sure, crossing the event horizon, the boundary of the black hole, means there's no turning back. Anything that passes this point is doomed to spiral inwards towards the singularity, where it will be stretched and compressed in a process scientists call spaghettification. The more mass you place into a small volume of space, the stronger the gravitational pull gets. According to Einstein's general theory of relativity, there's an astrophysical limit to how dense something can get and still remain a macroscopic three-dimensional object. Exceed that critical value and you're destined to become a black hole, a region of space where gravitation is so strong that you create an event horizon and a region from within which nothing can escape. No matter how fast you move, how quickly you accelerate, or even if you move at the ultimate speed limit of the universe, the speed of light, you can't get out. People have often wondered whether there might be a stable form of ultra-dense matter inside that event horizon that will hold up against gravitational collapse, and whether a singularity is truly inevitable. It's a reasonable thing to wonder. As we simply cannot access the region interior to the event horizon, we cannot know the answer directly. Nevertheless, if you apply the laws of physics as we know them today, you cannot avoid a singularity inside a black hole. Here's the science behind why. To understand this, let's delve into the concept of density and gravitational pull. Imagine compressing an object with the mass of the Earth into a sphere just a few centimeters across. The gravitational pull would be so immense that it would warp space-time to create a black hole. According to Einstein's equations, once you cross the event horizon, the equations predict an inevitable collapse of matter to an infinitely small point. This is the singularity, where density becomes infinite and the known laws of physics break down. Even the most advanced theories like quantum mechanics and string theory struggle to explain what happens at this point. A neutron star is basically an enormous atomic nucleus, a bound-together collection of neutrons that's even more massive than the Sun, but contained in a region of space just a few kilometers across. It's conceivable that if you exceed the allowed density at the core of a neutron star, it might move on to an even more concentrated state of matter. A quark-gluon plasma, where densities are so great that it no longer makes sense to consider the matter in there as individual, bound structures. Under these conditions, not only up and down quarks, but heavier, normally unstable quarks may become part of the stellar remnant's interior. It's worth asking an important question at this point. How is it that we can have matter at all inside the core of such a dense object? The only way for this to be possible is if something inside the object is exerting an outward force on the material exterior to it, holding the center up against gravitational collapse. For a low-density object like Earth, the electromagnetic force is enough to do it. The atoms that we have are made of nuclei and electrons, and the electron shells push against each other because we have the quantum rule of the Pauli exclusion principle, which prevents any two identical fermions, like electrons, from occupying the same quantum state under any circumstances where there isn't an internal source of radiation pressure. Like the pressure that arises from nuclear fusion processes inside of active stars, the Pauli exclusion principle is one of the primary ways that such an object resists gravitationally collapsing any further. But there's a key realization in the mechanism that prevents matter from collapsing down to a singularity. Forces must be exchanged. If you attempt to visualize it, force-carrying particles, like photons, gluons, etc., must be exchanged between the various fermions in the interior of the object. Here's a refresher on the basics of how our quantum universe works. All of the matter we know of is made fundamentally out of discrete quantum particles. These particles come in two types: fermions, which obey the Pauli exclusion principle, and bosons, which do not. Electrons, quarks, protons, and neutrons all fall under the category of fermions. Gravitation, which we believe, though aren't yet certain, is inherently a quantum force, can be well described by general relativity up until we deal with singularities. Any non-singular state can work within the framework of general relativity. In order to resist the inward pull of gravity, some quantum exchange must happen between the interior and the exterior of a volume-containing object, otherwise everything will continue to collapse inwards. However, those exchanges, regardless of the force, are fundamentally limited by the laws of physics themselves, including both relativity and quantum mechanics. As we delve deeper into the mysteries of black holes, there's one concept that stands out as both awe-inspiring and terrifying, known as the event horizon. This point, where space flows faster than light, creates a region where all paths lead inward. The event horizon marks the threshold where our current understanding of the universe ceases to apply, and a new uncharted territory begins. Anything that crosses this threshold is lost to the universe, forever hidden from our view. This includes light, matter, and even information, leading to profound questions about the nature of reality and the ultimate fate of anything that ventures too close. Is there a force, a principle, or an effect that could defy the inevitability of singularity? To avoid a complete collapse down to a singularity, we would need to discover a new force, one that can propagate outwards faster than the speed of light, challenging the very foundation of relativity. This hypothetical force would need to operate beyond the foreknown fundamental forces: the strong nuclear force, the weak nuclear force, the electromagnetic force, and gravity. Scientists and theorists around the world are exploring these possibilities, using the most advanced technology and the sharpest minds to probe the depths of black holes and the fabric of space-time. Could this new force be the key to unlocking the mysteries of black holes? Could it provide answers to the questions that have eluded us for so long? As we wrap up our exploration of black holes, we must confront a sobering reality. Quite simply, that scenario conflicts with what is presently known about our physical reality. So long as particles, including force-carrying particles, are limited by the speed of light, there's no way to have a stable, non-singular structure inside a black hole. If you can invent a tachyonic force, which is to say a force mediated by particles that move faster than light, you might be able to create one, but so far no real tachyon-like particles have been shown to physically exist. In fact, in every quantum field theory where they've been introduced, they must decouple from the theory, becoming ghost particles, or they exhibit pathological behavior. A singularity. At the center of every black hole is an inevitability. There can be no real particles, structures, or composite entities that survive a journey into a black hole. The journey into the heart of a black hole may be impossible for now, but the journey of understanding them is far from over.